Well, thank you all for coming. So I'm I'm actually a bit nervous because I'm talking, in front of a lot of like committed research geologists here, and I'm used to talking to engineers from a point of view of being the only geologist in the room. So there's a certain amount of like, yeah, yeah. I know what I'm talking about, but right now I'm not sure I know what I'm talking about compared to you guys. Um, so a little bit of my background here that I think Dave didn't say. I have a degree in geology, a bachelor's degree in geology. After that, I decided to go to engineering school, and I went to the mining engineering department just because I thought it would be easy to get a job afterwards at that time. And then I got pregnant and I decided it wasn't so easy to do another bachelor's degree after all. So I changed to a master's degree in mining. And then when it came to a thesis, someone suggested that I do geothermal, and I've been doing geothermal almost all the time ever since. With 1 year out, I worked as an environmental engineer, and then I went scurrying back to geothermal. Did a PhD, and anyway, worked in the industry and worked in the university, and ended up in Iceland. So yeah, that's me. And so it's somewhat of a mixed bag. Okay. Now today, what I want to do is just talk about, sorry. Just talk about how high temperature geothermal systems work. What I've found is in Europe in general, and I think the UK as well, I know you're dealing with lower temperature geothermal systems, and you know a lot about this, and you know a lot about rock properties and the thermal and mechanical properties of rocks. Shall I shout? And high temperature geothermal systems, and by that I mean systems that have a near boiling point, essentially, are slightly different animals, really, and quite complex animals. And to generate electricity from these systems requires a really multidisciplinary effort. So everything I mentioned today is actually by itself really simple, but all these elements and all these disciplines kind of come together to build our understanding of how high temperature systems work. So my approach is that I'm not looking at any one system. I'm just taking the kind of main elements of any high temperature system, kind of a little bit based on Icelandic ones, I think, because conceptually they're the easiest. And then I'm going to go through using this synthetic or conceptual system, if you like, and just explain the characteristics of these that we use to describe any of these sort of high temperature geothermal systems. Right. Boy, that was a long-winded explanation. Oh, I just shut that. Wow. Okay. So here we go. So there's three things that we need for a geothermal system, right? We need water because the water carries the heat. We need some permeable rock that the water travels through and picks up the heat. And we need a heat source, which is some sort of magma, usually moderately close to the surface. Okay. So these are the three things that we need for a high temperature system. And the water essentially permeates the rock, and we're talking mostly meteoric water recharge to these systems. It travels down until it heats up to the point where it becomes buoyant, and then it comes back to the surface and comes, essentially when it hits the surface, it'll come out as hot water or steam. Okay, so let's look at even now how we'll start looking at the characteristics of the circulation. So you'll notice that I didn't draw the arrows like actually touching the magma, like the water coming down. I didn't actually draw going as far as the magma. And that's because the water will travel in open pores, through open pores or through fractures in the rock. Now, on the other hand, the magma in the rock will intrude, but then it'll start to soften the rock around it and partially melt some of this rock. And so if we're thinking about the water traveling through fractures, that implies that the rock is brittle. So if the magma is partially melting the rock, then that's becoming ductile and it can't fracture because it's got a certain amount of liquid with it. I mean, it depends on the strain rate, so you can argue that. But if it's just sitting there, it's not going to fracture. And so this creates this sort of boundary zone, and I've drawn it here as a line, but obviously it's more of a zone, I would say, which is the transition from brittle behavior to ductile behavior. And the water, generally we consider most of the water won't go past this brittle ductile boundary. So that kind of limits the depth of circulation. In Icelandic systems, that'll be 6 to 8 kilometers maybe. And of course, as you get away from the magmatic geothermal system, it gets a bit deeper, down to about 10K maybe. And what are the consequences of that for heat flow? So in the ductile zone, that means you have conductive heat flow in the rock. So the heat is just being conducted through the solid rock. But above that, in the geothermal system, you have convective heat transfer, where the water is actually transporting the heat, okay? It's picking it up out of the rock, and then the majority of the heat is traveling in the water. Okay, let's see what happens next. Okay, and how do we kind of describe the thermodynamics of the reservoir? Well, essentially in terms of temperature and pressure. And temperature-wise, we can contour the temperatures in the system. And, well, obviously, these are isotherms, okay, lines of equal temperature. And typically, you have the isotherms. So these, okay, let's start again. These isotherms are the typical sort of temperatures that we would find in a high temperature geothermal system like in Iceland or in New Zealand. The 300 C isotherm is a nice hot reservoir temperature. And the 100 isotherm, of course, is the boiling point of water at the top of the system, actually essentially at atmospheric pressure. And I just realized I've actually obliterated the 100 isotherm. I'm sorry. So we essentially think, like in my mind, when I'm thinking about how a geothermal system works, I'm thinking about these isotherms and what shape they are. And essentially these will be more or less perpendicular to the direction of flow. That makes sense. They're gradients, in other words, or across perpendicular to the isotherm is the thermal gradient in the system. Okay, I think let's see what happens next. Okay, in terms of pressure, we have to find a way of thinking ideally how the temperatures in the upflow are characterized. And the simplest way of thinking about that is thinking of the temperatures always being at boiling point at the pressure that exists as you go down through the system, okay? And this is called the boiling point for depth curve, because as the pressure increases from the weight of overlying water, then the boiling point goes up. But we assume that at any point in the system, the liquid is sitting there right at boiling point. You know, you drop the pressure by a fraction of a bar and it'll start to boil. And that's an ideal curve, obviously. In real life, you kind of see the temperature profile hitting boiling point, and maybe it might reverse a little bit, then to hit boiling point again. But in an ideal world, sometimes you do see this, you see a boiling point for depth curve. The thing to remember about this is that if you have a lot of total dissolved solids in the water, then the boiling point for depth will increase. It will increase the boiling point of the fluid. And if you have a lot of gas, and CO2 is the most common gas in geothermal, then that will decrease boiling point for a given amount of CO2. What have I left out? Yeah, so essentially the maximum temperature at any depth is limited to the boiling point for depth curve. And so, as you can imagine, if you drill a well in the hottest part of the reservoir, then where it intersects the isotherms is going to be the thanks, Dave. Thank you. Yeah, up here, so these are going to be the temperatures that you plot in the well. In actual fact, it's a wee bit more complicated than that, because you have to kind of interpret the temperatures that you get in the well, but ultimately you should end up with something that's the actual reservoir temperature at those points. If you want to know more about that, then ask me after the talk. Okay, so far I've just talked about the water flowing through the rock, but I'd like to point out that some rock is more permeable than other rock. Okay, there's different permeabilities exist in the subsurface, and essentially the hot water obviously will flow through the most permeable rock, and if it's doing that, then that in turn affects the isotherms, right? So if, for instance, you've got a low permeability rock at the top of the system, and the next slide also shows how this is very common, then the hot water is going to come up and kind of flow sideways. And then the isotherms are going to get more sort of spread out horizontally in a sort of a mushroom shape. And I should have drawn one here. If you drill through this part of the system, you're going to get, say, here's 200 degrees. You're going to keep going. It's going to be a wee bit hotter there probably, because it's getting towards 250. And then it's going to get cold again. And then you're going to go down. It's going to even get colder. Okay, and you go down, and then it hits 200, 250, and then it starts to get hotter again. You're like, damn, what's happened? And what's actually happened there is that you've drilled into this sort of horizontal flow of hot water, which is not always a bad thing. You know, that might be perfectly fine. If you can get sort of 250 degree water just here, that's not bad. If it's permeable, that's fine. Provided, of course, provided it'll keep sucking hot water this way and not sucking cold water that way with time. So essentially, the permeability structure is related to the lithologic structure. And really, this is why when we're this is why we're so interested in the geology of the system, because that's our first guess at what the permeability structure of the system is, and how hot water will flow through the system. then there's other things as well, like how the rock will be altered by the hot water, in other words, the fluid rock interaction and other things. But the primary reason, really, or the effect of geology is to give us our permeability structure for the hot water flow. Okay, and as I said before, there is a common reason why I'm talking about a low permeability zone at the top of the reservoir. And that's because the rock over the upflow will be altered. And it will be altered by the hot fluid reacting with the minerals in the rock and basically turning them to clays. Okay. And clay is actually quite low permeability, and it's also got a low electrical resistivity. So when you're doing electrical ground resistivity measurements, then you're going to get this low resistivity zone, which defines the top and the bottom of that zone here, defines the top of the reservoir. And underneath it, you see this sort of more resistive rock, which you hope is your hot reservoir. It's a wee bit of a gamble, but it's the best first guess at the subsurface sort of reservoir structure that you usually make. Okay, so the next thing I want to talk about is the chemical composition of the reservoir fluid. And so there's three things that affect this. There's the source, there's the reaction of the fluid and the rocks, and that changes the composition. And then there's also boiling, which will concentrate some things in the liquid. Gases will go with the steam. And then also mixing, because then you might get groundwater or colder water coming into the system, mixing, and then you get different minerals precipitating as well. So in terms of the source water, I mentioned meteoric, which is probably the most common. There's also systems that have seawater recharge, either partial seawater contribution to the system or almost 100%. So on the Reykjanes Peninsula in Iceland, there's the Reykjanes geothermal system right at the end of the peninsula, and that's like right on the coast, it's right on the mid-ocean ridge, and essentially that's a seawater system. And you can tell by the amount of corrosion around the surface equipment as well. And essentially, if you're dealing with sedimentary basins, of course, then it'll be connate water, like the original water and the sediments. And you do get some magmatic component as well, a little bit of magmatic component in a lot of high temperature systems. Now, fluid rock interaction. Okay, for a start, that's very temperature dependent. And in fact, if you look at the fluid chemistry and the ratios of some elements, then you can use that to estimate the reservoir temperature at greater depths than you've sampled. Or you can use this if you're checking, sampling your reservoir fluid from the wells. You can check that what we call the geothermometer temperature, which we get from these ratios of different elements in the water. You can check that against your measured temperature and go, okay, have we got an agreement here? And if you don't, then you might suspect that the water's come from somewhere else in the reservoir quite fast and come into the well, for instance, or you think of some other explanation. And also, yeah, there is another method we use, which is called fluid inclusions. So you look at the way waters goes from liquid to two-phase and very small inclusions in the actual minerals. And then you can tell what temperature those minerals formed at, essentially. Okay, and when it comes to boiling and mixing, that's really interesting. It it relates mostly to precipitation of minerals in boiling zones, for instance, and in wells, and also release of gases. So usually the geothermal gases, when the liquid boils, go with the steam, so you get CO2 and H2S are the main ones. Then a lot of minor gases like ammonia, methane, sulfur gases, all sorts of things. And yeah, so this actually will affect production, and I'll mention that in a minute. Okay, so I mean, the chemistry of geothermal systems, as you might have guessed from that previous slide, is very complex, and there's like lists of elements that you can analyze, and complexes that you can analyze for. But the very first thing, this absolutely simplest geochemical model that we all like use all the time, it's in the back of your head, is that we can classify these waters by three main anions. Okay, there's chloride anions, there's bicarbonate, and sulfate. And very few waters just have one of these. Usually most geothermal water is kind of a bit of a mixture, but one of these is dominant. Okay, so we classify these by the dominant anion. So the chloride water is what we call the deep reservoir fluid, and that's what we want to produce. And then the bicarbonate water is usually kind of what we'd say were marginal waters. They're still warm, they can be over 100 degrees, but because they're a little bit cooler than the water in the upflow, the CO2 gas will preferentially dissolve in these cooler waters. And then sort of over in the very shallow parts of the system, you get sulfate water. And I think the next part of this, yeah, okay. So I'll just describe each of these in turn. So the chloride water is a neutral pH. So that's nice, it's not corrosive. This is the production target. This is what you want to produce. If this water gets to the surface, which it does quite often, like through, say, a fracture, you can get a path directly to the surface. You get this discharging at the surface as these really like nice, clear, blue-green sort of boiling springs and geysers, and it precipitates silica. So you get white silica terraces, and you know, it's very beautiful. It's very pretty, really nice to look at. The bicarbonate water, as I said, forms because the CO2 dissolves preferentially in the cooler waters at the margins of the system. And if this gets to the surface in the form of springs, then it deposits travertine, or calcium carbonate deposits. And sometimes you see springs with a mixture of calcium carbonate and silica deposits, because, as I said, these waters are mixed often. These are the end members that I'm talking about. And then the sulfate water is actually from the H2S gas that, as it boils off the deep fluid, it hits the groundwater and it reacts with the oxygen in the groundwater. So you get H2SO4, sulfuric acid. So these sulfate waters are low pH. And what happens is that the sulfuric acid actually steals the metal cations out of the rock. And what you're left with is clays, hydrothermal clays, and which are potassium and aluminium silicates. And essentially they just turn to mud. And so when you get acid or low pH fluids, then this is when you see mud pools. So anytime you see bubbling mud pools around geothermal areas, you can pretty much bet this is fairly acidic water. Okay, and you get steaming ground, or at the other, like extreme discharge end of the system, you'll get fumaroles, like really high pressure steam, really thundering out. You know, it's quite impressive too, actually. Okay, oops. All right, I'm not sure if this video worked. Okay, but anyway, so first of all, I'll just talk a little bit about CO2 here. So usually CO2 is like the most common gas in geothermal, right? It can just bubble out of the ground, like in this top, what is it, left-hand photo here. So that's actually CO2 bubbling through cold water. It's just a cold water stream, but it's over a geothermal system. And all along this stream, there's some hot pools, but there's this CO2 just basically bubbling out of the ground. That's quite a freaky area, actually. And in some places, the CO2 just comes straight out of the ground. And if it does that, then it kills the vegetation. And I don't have any photos from that at Napa. Well, I do, but I didn't put them in. But there's a brilliant example of that at Mammoth Lakes in California, where there's this area of dead forest. And essentially, this is from CO2 in the soil. You can't camp there because you'd probably die from sleeping there. And you've got to be quite careful. There's also an area in Rotokawa, right, where there's a geothermal area in New Zealand, where there's a bit of a dip in the ground, and small animals like go into this and they just die. They're just suffocated straight away. So yeah, you have to be quite careful of CO2. And then I had this video. This is a boiling pool. Oh, it works. Oh, yay. So this is a boiling pool in a stream. And you can see, actually, there's a couple of things to note here. So this is a warm stream. And yeah, it's not on loop. I'm sorry, because I had to transfer the file to this computer. This is a cold or warmish sort of stream, like this geothermal discharge further upstream. But then there's this area here, and this is a really hot spring. Like, I would think this is boiling, but I also think it's got a lot of CO2 in it, just from the way it's kind of fizzing. And you can see it's like all this is ion alteration, basically. So I just thought that was an interesting kind of phenomena, really. But yeah, it was really hot. I tried to put my finger in there, and it was like a wee bit hot. Okay, but here I'm not sure what happened. Oops. Okay, where am I? Sorry about that. I think we lost a few photos on the transition here. Let's see. Oh, that's a shame. Okay, so I had a few carbonate deposits here. I'll try and find it afterwards and add it to the later. I won't go looking them up now, but just some really good examples of calcite that are deposited in a well liner due to flashing, and in a steam water separator. So basically from boiling as well, from flashing. And this is a huge pipe. It was about, I don't know, probably about that diameter or so, I suppose. And honestly, it was down to a hole about that big from the calcite deposit in the pipe. So it's pretty extreme. And the way that the mechanism of carbonate deposition is if you've got aqueous CO2 and then you've got like calcium ions in the water, and of course this plagioclase for a start, and then calcium from other minerals. So there's pretty much always enough calcium. Then you get carbonate precipitated. Okay, and now the other thing is the other very obviously common element, because it's the most common element or common chemical in the crust, is silica. silicon and oxygen. And the silica is silica content is solubility is dependent on temperature. So the higher the water temperature, the more silica it'll dissolve out of the rock. Okay. So we can use this as a geothermometer also to estimate what the temperature of the water was in the subsurface. It equilibrates quite fast. So if you get something that appears to be near reservoir temperature, you know the water's come up quite fast. Or you can think it's equilibrated on the way. There's a bit of a science there in silica geothermometers, and there's a few different types of SiO2 crystal structure, so you've got to kind of know what you're looking at there. But anyway, silica in water is used, in geothermal water is used as an indicator of some subsurface temperature. When you're looking at silica deposition around springs, then it's very beautiful. You know, it's very pretty. You don't want to walk on it because it breaks the very delicate structures. And another thing is that actually fossil silica deposits from hot springs are very interesting to geologists, because they'll tell them something about the flow regime in the past. And you might think, okay, but it's a fossil system, who cares? Well, it really cares if you're looking for epithermal gold deposits, because it'll tell you something about the way the system was working. And geothermal systems often will be depositing gold in the subsurface. And if you're looking for this gold, which is called epithermal gold because it's shallow in the crust, shallow gold deposition, then you're very interested in the way that, in what the surface features were doing, or, you know, what the record of the surface activity is in that geothermal system. Amongst other things, of course, you're also interested in the structure, the orientation of the veins, and you know, structural geology becomes very important here, Dave. Right. Okay. So the other thing, in terms of geothermal production, silica is a total pain in the neck, because it's temperature dependent. So as soon as the geothermal water comes up, you take some energy out of it, you try and do something with it, it drops its silica at you. And so you've got to deal with this. You can use an anti-scalant, which is kind of expensive. You can work over the wells every so often, but silica scale is pretty hard. So, you know, it's can be a pain, or you can actually try and precipitate it out before you, say, inject the water into the re-injection system. So these are all ways of dealing with silica precipitation, but it can be a real pain. Or actually, yeah, the other thing is you can re-inject at a higher temperature where you're above the silica saturation index. But if you do that, you're re-injecting energy that you just went to a lot of trouble to get out in the first place. So that's not a popular option. Okay, last thing here about surface features is, here we have this hot springs, the H2SO4 water, the acid sulfate springs. And I'm sure you've all seen these sort of springs, right? Typical mud pools, essentially. So you can just look at that and you can go, pretty good guess that that's acid, all right? And so what's happened is that the H2S has reacted with the O2, created H2SO4, which has stolen the cations and left behind the clays, which have turned to mud. And off we go. We have geothermal areas. And you don't want to, like, you know, walk too close to this stuff, because even on the surface, like, it might seem kind of not totally hot, but, you know, it this far into the ground, it'll be boiling. And if the ground's quite soft, you can sink into it. It's really, this is really dangerous. All right. So one thing we're kind of interested in is what is the total amount of energy coming through the system? And it's the summation of all these different types of surface feature, okay? We look at just what's coming through the soil because, as I just said in the previous slide, it can just be like just soil like this and it's warm. And so there's obviously heat coming through it. If it's dry, then that's conductive heat, and you can calculate that by measuring the temperature gradient and assuming or knowing or assuming a thermal conductivity. If even if you can't see it, often there is some moisture coming through there, though, some evaporation. It doesn't have to be boiling, it can just be like dampness evaporating. And you can tell that quite often if you just put your hand on it and you can feel it getting damp. So that calculating the heat flow then becomes a little bit trickier, but you still can do it. And then you've got the heat discharge from water surfaces. So you've got evaporation from the water surface, you've got radiation, conduction, what else? And then you've got the turnover from a vigorously boiling surface. And there's like formulas that you can do all that. You've got steam vents. So you've got to calculate the velocity of the steam and the energy in it. And then you've got how much, well, the heat, and then you've got the energy. And then you've got overflows from liquid features, so springs and geysers, so you can measure the temperature and the flow, and then you've got the energy. And then you've got subsurface seepage, which is actually a little bit harder to figure out. But you know, sometimes you can do it just by temperature measurements in rivers, drone mapping of temperature differences in water surfaces. But, you know, putting all that together is still, there's going to be a big margin of error, but we are interested in that. And I'll come to why we're interested in that, I think, in a few slides. Okay, just some pretty pictures of surface features. Actually, I might just move this away here. So these are carbonate travertine terraces in Turkey. This is actually, there was a Roman spa at the top of this hill here with, you can still go swimming in the hot pool actually, that's there. And this picture on the top right, it's also predominantly calcite deposition. But I put that there because it shows how these deposits can preserve what was happening at the time. So it's a little bit small. I can't make it any bigger at the moment. Can you see anything there? Can anyone see anything there that like might indicate what the biota was at the time? I'm sorry, it's so small. Yeah, you might not be able to see. Okay, so this is a skeleton. That's the skeleton of something there. See that? No, it's not. Yeah, I don't have a scale. I think it might be a rat or something because it actually goes on here. Like, first of all, I thought it might be a bird, but it's actually got a tail. Like you can see backbones, and I think it's a rat. And here, oh, I can't shift it. Here's a frog as well. Some extremely unlucky frog jumped into hot water, I think. And these are all ants, these black things. So yeah, so this is preserved in the fossil record. And pollen is also preserved actually. So it's of interest to paleontologists. And let's see if this works. Yeah. Okay, so this is Strokkur geyser in Iceland. And actually it's just about to erupt and you can see the surface of it kind of like getting a bit agitated. And that's because there's actually a steam bubble coming up and then collapsing, and then gradually the bubble develops more until it erupts and it pushes the column of water ahead of it, essentially. And this one went off twice very closely together. So yeah, I think they're one of the nicest geothermal features. They're really, really pretty. Very impressive. Yeah, and of course, one of the, I mean, drones are just great, right? You know, drones are lovely. You can see things, have such a beautiful overview. And geothermal's like no exception. So drones let you, give you access to places that you can't walk to because they're too dangerous. In this case, on the left-hand side, this is a geothermal lake and it's surrounded by blackberries. I mean, blackberries this high and really mean, you know, just you do not want to go through these things. And then it gets dangerous because actually you can't see where you're walking either. And you really don't want to fall into a hot pool. You know, it's really nasty. So with drone mapping, this is, I believe this is temperature and this is, yeah, heat flow here, heat flux from that feature. And it's all calculated from the data collected by drone. And so it's much safer. And it gives you a kind of a good overview. And this here is from an area in Iceland. And we wouldn't have seen half of these features in the middle here. They're small features, but they kind of all add up. You know, the disadvantage is that if you look at this feature at the bottom here, it can't do anything about steam, right? It can't measure through steam. And these sort of plumes here are steam. It was quite a windy day and the steam was blowing all in one direction, which was nice. So you got a good picture of the sort of edges of this feature, but not down here at all. But, you know, it's still, even if you're just looking at the structure of the discharge, and this tells you something about the shallow permeability, right? It's really like in a line here. So these features are, yeah, kind of in a line, and it lines up with the sort of axis of this valley that this is in. And the good thing about this also is that you can carry out the survey annually or every 5 years or something, and then you can monitor changes in the system. And they may be natural changes or they might be due to production. Okay, how am I going for time? What's the time? It's all right. I got 10 minutes. Really? Wow. Okay. I should stop talking so much. Okay. So wells are really interesting because wells are our connection between the surface and the reservoir. Okay. They're the one thing, they tell us everything we're going to know about the subsurface. And at the same time, they create this artificial sort of permeable channel. So any data we get out of a well has to be interpreted in some way. Anyway, so how did this sort of start? So actually earlier than the 50s, but this was the earliest photo I had of a drilling rig. And as you can see, this is a pretty small sort of truck-mounted drilling rig, and it would drill to less than 600 meters deep. And at this point, they were drilling into one of these horizontal outflows, so you didn't really want to be more than 600 meters anyway. And yeah, that's from the 1950s. So now we would routinely drill to 3,000 meters. You know, maybe less, depending on what system you're dealing with, but 3,000 meters is, yeah, kind of to be expected. It's not surprising. And your cost, I guess, is anywhere between, this is US dollars, like 3 million. I don't know, if you go over 10 million, you might be worrying about your job. And the hottest geothermal well has been drilled in Iceland. Actually, the final temperature is not ever known. It'll never be known now because the well is closed. But nonetheless, very exciting and very interesting. It was drilled to 4.6 kilometers. I think it was 4.6. Yep. Underneath the existing production field at Reykjanes. So underneath all the existing production wells, they drilled this well slightly directionally to 4.6 kilometers. It was warming up, and the last temperature measurement was around about somewhere between 450 or 460 degrees C. But the fluids are quite corrosive, and the casing corroded at about 1400 meters, and essentially that the well was stuffed, really. You couldn't do much with it. So I think they've either abandoned it properly, like sealed it up, or they're going to, which is a bit of a shame, but still it was super interesting. And what it showed was a really high permeability zone, very deep, which was quite unexpected, and that it was very hot. Okay, and you know, I'm not sure. A good question is, how many wells might you expect for a sort of a given development? So here's all the wells drilled in Iceland between 1979 and 2019. I haven't added up how many actually. I think that's total well depth. Okay, so you've got a kind of, that's not exactly the amount of wells, but if you think probably the average depth would be maybe between 2 and 2.5 kilometers, you can work out how many actual wells there would be drilled there. I think, let's see, did I go? Oh, no. In terms of a single development, Hellisheiði, which is a 300 megawatt development in Iceland, that's 300 megawatts of power and almost the same of thermal, I think, has about between 50 and 60 production wells. Waireki in New Zealand also has around 60 production wells for 400 megawatts. It's a little bit lower temperature than Hellisheiði. And then the amount of re-injection wells depends on the enthalpy of your fluids. So if you've got a lot of steam, if the wells are very hot, you're not going to re-inject much water. If you have lower enthalpy, less steam, then you're going to need more re-injection wells. But I think Waireki has about 30 or so re-injection wells, but they're not all used at once. They've got, like, they keep spare capacity in case they need it. So yeah, for a big development, you might be looking at around 60 wells. So, you know, it's quite a lot of drilling. Alternatively, you could just, if you have one well, you know, you can still have a small power station, which will still maybe provide enough electricity for, I don't know, in the order of like thousands of households. So, okay. So, what happens when you get this water to the surface? Okay, so this is the sort of, if you've got a two-phase system, essentially. So this is the most complicated system. So you have, I'll do it up here. So here's your production well, and you have a mixture of steam and water coming up the well, because even if it's liquid at the feed, as it comes up the well and the pressure drops, it'll start to boil. Okay, so you have steam and water coming up the well, and this goes into a separator, a steam water separator. And essentially, you have steam coming out, which will go to the turbine, and then you can have hot water coming out here. Well, actually, there's different separator designs, but conceptually, this is fine. So then you can actually take this hot water to a lower pressure separator, because remember, it's boiled at this higher pressure, and then you can take this water here, and it'll boil again at a lower pressure. So it'll boil at lower pressure, and you can take that, well, you can take it to another turbine, or you can take it into a different stage in the same turbine. That depends on your design and your engineering philosophy. And then you still have some separated geothermal water. Okay, So you can take that geothermal water, you can take more heat out of it, like directly with cascaded use, and I haven't drawn all those things in here, but you can do that, or you can just re-inject it. Okay, so it goes to an injection well. And how many stages of separation you have just depends on your system. That's up to the engineers. It's depends on the pressure and wellhead pressure and the temperature of your system. Here, there's 3 separators. You can see 2, 3 here, and you can see how big they are. Like those are people down there. So these are massive machines. Okay, so the water comes, or the steam comes off the end of the turbine, and then it goes to a condenser. It's condensed and it goes to a cooling tower. So this water vapor evaporates off here and goes into the air. And then, okay, some of the water comes down here and it's actually taken back to the condenser. So it'll condense the next lot of water. So it's this kind of open loop, really. And then there's always spare water. So this will go off also to re-injection. And whether or not it's mixed with this separated geothermal water, again, depends on the way you've designed the system. Okay, so that's steam turbines. And then there's also binary, which is slightly lower efficiency, but it's very reliable. And also you can use lower temperature geothermal water, so it never has to boil. You can go down as low as 117 is the lowest temperature well I've seen producing binary power, but probably even lower. Again, it depends on your system. So you just bring the water up the well, you put it through a heat exchanger and you re-inject it, or do something else with it, depending on the design of your system. On the other side of the heat exchanger, you have a fluid with a low boiling point. And that can be any number of chemicals. It can be pentane. It's commonly pentane, or any other. There's other kind of refrigerants that you can use as well. And again, it depends on the actual design of your system. But this working fluid goes through the heat exchanger. It boils, and isopentane will boil at around 34 degrees. So we're talking, you know, really quite low temperatures, and it goes to a turbine. The turbine generates electricity, and at the end of the turbine, the pentane goes through a condenser and then comes back and it's heated up again, and so it's a closed loop. So these are simple in concept. They've obviously, the engineering expression is lots of valves and pipes and stuff, but you know, they're very reliable sort of systems. And so this is a condenser. It's this design binary is a air-cooled condenser on it, and actually most of it is just taken up with the condensing pipes. These are all fans, and they just draw cool air over the pipes with the isopentane in them, the condenser. Okay, and actually I should say this whole plant actually is operating off the separated geothermal water. So it's water that would normally have just been wasted, and it actually generates another 12 to 14 megawatts of power, which is a significant amount. Okay, so what happens when we produce from a geothermal system? Okay, so these are like reservoir issues. This is what reservoir engineers worry about. Okay, so let's see what happens here. So and I've got one production well and one injection well, just for simplicity. Yeah. What? Time. Okay, I'll go through the next 2 slides. Okay. Is that all right? Do you want me to stop? just shut me up, you know.